Now, I'm really very, very proud and excited that we could have Hector Geffner giving a keynote at the German KI conference. And yeah, Hector Geffner, I think it's not necessary really to introduce him, but of course I nevertheless will do this. He is a research professor at the Universitat Pompeu Fabra in Barcelona, Spain. He grew up in Buenos Aires and he did his PhD in computer science at the UCLA. And this was under the supervision of Judea Pearl, whom I guess everybody knows from his influential work on Bayesian networks and causality. Hector worked at the IBM Watson Center in New York and also in Venezuela at the Universidad Simón Bolívar in Caracas. Yeah, it's a little bit embarrassing when you look how time is running. Actually, Hector and I met in person in 2000 at the 5th Conference on Artificial Intelligence Planning Systems, AIPS, in Colorado. And I presented some ideas about rule learning from plans, and Hector introduced at this conference heuristic search planning. And I guess most of you know what came of that. It is one of the most well-known approaches to planning up to date. And the conference paper is cited more than 450 times, while the AI journal paper, where this approach was published a year afterwards in 2001, is cited more than 1,200 times. Hector is a fellow of AAAI and EurAI, a board member of the European Association for AI, former associate editor of AI and of Chair. He currently, I think, has an advanced ERC grant, and there he does research on symbolic representation learning for planning. This will also be the topic of the keynote, entitled From Model-Free to Model-Based AI, Representation Learning for Planning. Hector, thanks again a lot for coming, and the floor, or better the screen, is yours.
Okay, thanks, Ute, for the invitation, for the introduction. I wish I was in Bamberg. Let's see, okay, if I can. Okay, I try to share this. So thanks again. So too bad not to be right now in Bamberg and to enjoy all these beautiful sights, okay, that I can see in these videos. I hope that I'll be invited in the future again. The talk that I'll give today, as Ute said, has to do with representation learning for planning, and okay, more generally about a little bit about the state of AI between model-free and model-based approaches. Okay, so the plan for the talk is divided in two parts. One part is like a view, is to articulate two essential threads in a research, one that is concerned with learners, okay, that actually has more of the spotlight these days, and the other based on model-based solvers, okay? So I'll talk a little bit about that, try to contrast them, okay, what they have in common, what they have different, okay, also to draw some comparisons with system 1 and 2, okay, that we have heard about this a lot, to draw some conclusions about challenges, okay? Because one of the main challenges, okay, for many people, including myself, is that if learners and solvers have something to do with systems 1 and system 2, okay, in the human mind, okay, I'll talk about this later, okay? So one key difference is that system 1 and 2 are very well tightly integrated in the human mind, while learners and solvers, for the time being, each one is going its own way. And one of the key challenges I'll try to emphasize is about learning the models that the solvers use that normally are built by hand, and that's a big bottleneck. So basically, I'll go into these two parts. So the first part, actually, I talked about this a couple of years ago in ISHKAI, so there is even a paper that you may want to take a look if interested in this general view. The second part is a bit more technical, and I give references as we go along, okay? As Ute said, actually, I did my PhD at UCLA in the 80s with Julia Pearl. Interesting thing, at that time there was an AI lab at UCLA, but they were looking at us, okay, in particular at Julia, as he was not doing AI, that he was doing, as some people say, sort of statistics, okay, because AI was done by programming, and in particular by programming in Lisp. And if you had a Lisp machine, so much the better. Actually, at that time, it was very common, okay, to do a dissertation by picking up a task, analyze, introspect to an expert, okay, how the task is solved, okay, by people, and then to try to capture this reasoning in a program. Okay, so very, very interesting ideas came from this work, great books. Actually, one of the best books on AI programming was written by Peter Norvig, okay, that then, okay, became famous at Google, and also is the co-author of one of the most standard textbooks in AI, the one that he wrote with Stuart Russell. However, this idea of doing AI, okay, or making progress in AI by writing smarter and smarter programs, okay, ran into a problem, into methodological problems. These programs were good for handling a few examples, a few scenarios that the programmer had in mind when he wrote the program, but basically any new scenario, any completely new situation were out of scope for these programs, okay? So I will say that this is one of the main reasons that if we look back, we can see a methodological shift away from writing programs for ill-defined problems as understanding jokes or stories and things like that, and increasingly more to write algorithms for well-defined mathematical tasks, okay? So two of these family of programs, the ones that are focusing on learners and solvers, and actually both can be understood in a crisp way as computing functions, okay, that map inputs into outputs. The nice thing about these two threads of learners and solvers is that the algorithms, okay, that have been developed, okay, for doing learning, for doing solving, and so on, they are not tied to particular examples as these programs that were written in the past, but are tied to general class of mathematical models. So let me then talk a little bit more about these learners and solvers, okay? So if we, for instance, start focusing on learners, and in particular in the most famous ones these days, those that are based on deep learning and deep reinforcement learning, what these learners compute are actually functions, okay? The function, the structure of the function is given by the structure of the neural network, the so-called architecture, and the function itself is determined by this structure along with some parameters that can be adjusted by training, okay? So in the case of deep learning, that is a supervised method, okay, so the inputs may be an image and the outputs of these boxes, okay, that are learned, okay, may be a classification label or bounded box, okay, for the input image and so on. In the case of deep reinforcement learning, most commonly, okay, so the inputs to these boxes that I learned maybe states of different games like chess and so on, and the output will be something like the value of the state, a probability distribution of the actions to be done in this state of things of this sort. So the question is how these functions that do these mappings are learned, and normally in all these cases, the parameters are learned by minimizing some error function, okay? The type of error function depends on, again, so whether the learning is supervised or based on reinforcements. In the case of deep learning, the error has to do with error in the prediction, okay? What you predict and what is given in the training set. In the case of deep reinforcement learning, okay, the error has more to do with some internal consistency, the value of a state and the value of its possible successor states. In most cases in deep learning, okay, the way that this error function is minimized is by some form of a stochastic gradient descent, okay? And the results in this thread, I will say that have been pretty amazing, okay? So I will say that if a lot of the excitement in AI, okay, that we see these days is basically due to the big successes, okay, of deep learning and deep reinforcement learning, true breakthroughs in the history of AI, not only in image recognition or speech recognition and so on, but even achieving things like superhuman performance in games like chess and Go, and in some cases by self-play alone, okay? To me, that's pretty remarkable, even it takes, okay, a lot of time. And in some cases, these techniques are mixed up with some other techniques, okay, like Monte Carlo research and so on. The basic ideas underlying deep learning and deep reinforcement learning are not new, okay, for the most part, okay, they come from the 80s and 90s. So in the last few decades, we had more CPU power, GPUs, more data, deeper nets, and some really attractive problems when you can really show the progress, okay, that has been made. Okay, this, of course, does not mean that the singularity is near, that human level AI is near, or any of this sort. Okay, these deep learning and deep reinforcement learning have been shown to be incredibly powerful, okay, by doing things that was hard to believe, okay, that you can do these things and achieve these things by simple algorithms like gradient descent, okay. But there are some limitations, okay. One of them, of course, is that you need lots of training or a lot of data in the supervised case. A more important limitation is these systems that are built in this way, these boxes, these functions, okay, that are built in this way, normally they lack understanding, okay? So they can do translation, and many times they can do translation pretty well. They can write text, okay, that look very human-like, but there is no understanding at all, okay? So you cannot ask questions about the meaning of the story that is being translated, okay? That's one thing. The second thing that is very hard to understand, okay, exactly why they do, if you want to explain why they do or to understand, and this is key if you really want to trust these systems. So I would say that one of the reasons that we don't see yet, and probably are not gonna see in the short term, self-driving cars deploy in the streets, let's say in Europe, okay, is because these systems are very, are not trustworthy, okay, because they're black boxes and they have some trouble making sense of new situations. That is, okay, what people in deep learning or machine learning in general call out of the distribution. So problems, in some sense, that are not well represented in the training distribution. In those cases, you have to make sense of this situation, okay? And this is what the systems so far have failed to do. Okay, the other thread that I mentioned is about solvers. Okay, solvers can also be understood as computing functions, but they compute functions in a different way. Okay, for each input, they compute the value of the function. For that output, they don't compute the function f itself, but in this lazy fashion. Okay, so for instance, a solver for SAT accepts as input a formula in conjunctive normal form, outputs a 0 if the formula is unsatisfiable, and 1 if it's satisfiable. Okay, classical planner may accept a planning problem as input, a domain, an instance, and so on, and in the output may produce a sequence of action, a plan that solves the instance. Okay, you can have Bayesian network solvers, okay, inference engines, okay, that will take a Bayesian network, will accept queries about these networks, like what is the probability of this variable, okay, or the distribution of this variable given these observations, and the solver is supposed to answer. There are many other models and solvers that we consider in the eye, okay, like constraint satisfaction problems, Markov decision problems, POM-DPs, and so on. A characteristic of this thread is that these models are not about particular instance, particular examples, but about certain type of mathematical structures. So these models and solvers agenda, okay, in some cases they deal with very expressive models, okay. Some people have said, okay, like models like POM-DPs, where an agent is dealing with a dynamic environment through noisy sensors, okay, that give you partial information about the state that moves the stochastic and so on. These problems, okay, having a good solvers for POM-DP will go a long way to having something like an AI complete algorithm. Even certain forms of learning can be expressed as the solution of certain type of POM-DPs. Indeed, learners can be regarded as solvers too. Okay, they are solving a different type of model because they are solving a continuous optimization problem, basically TensorFlow and this type of deep learning shells. So they provide ways for you to specify the functions, the architecture, to specify the loss functions, and to play with the algorithm, okay, to achieve these minimizations. Okay, there is one way, okay, to look at learners from the point of view of solvers as well. So in terms of the complexity, all the models that we care about in AI, okay, so they are NP hard, okay, and one characteristic that is different from the boxes that we have seen before for deep learners and deep reinforcement learners, the inputs normally in this type of solvers, okay, are not bounded in size, okay? You can fit problems, and normally you analyze the complexity of family of problems as in terms of inputs, okay, that grow in size, okay? And the challenge in solvers, the computational challenge, of, even though that these models are computational hard, how to make these solvers work, that is, that they will not break just because the problem has many variables, because there are many problems that have many variables and still are not necessarily hard. So in a sense, that's the challenge more or less in this type of agenda. So going back to the contrast between learners and solvers, okay, and the idea that both can be regarded as computing functions. So one key difference is that in learners, you require experience and slow training. After that, you compute the function here, this box F, and then you can map inputs into outputs very quickly. In solvers, on the other hand, okay, you are dealing with completely new problems, okay, out of the box, and compute the value of the function just for the input that is given, okay? And that takes time, okay? Actually, in the worst case, there's, we mentioned this at NP hard problems, okay? So in one way to look at this is that basically the solvers, they have to think a bit, okay, about each new input that is actually represented in new problems, while in the case of learners, they did most of the effort in the training. After training, okay, the box is already built, is the neural network with the weights already adjusted. All you have to do is to feed inputs, and you get the outputs in linear time in the size of the network. Now, thinking is hard, and I will joke that these days is not very much in fashion, but somebody has to do it, okay? So I will devote a few slides to see how one can do effective thinking in some problems that are related to planning, particular problems where, okay, our group, okay, has something to do. So I'll go quickly over this, and I'll come back, okay, to the learners and solvers. Okay, so one of the problems, okay, that illustrates well this contrast between learners and solvers, okay, one that basically require training that is slow, but they are fast. On the other hand, these solvers, okay, that consider just one problem at a time. One of these problems is classical planning. So one of the problems, okay, are normally covered in any textbook of AI. Classical planning can be thought as a problem of finding a path in a directed graph where the number of nodes in this graph is exponential in the number of problem variables. So basically, you're trying to find a path in huge graphs of exponential size. And the question is how to search for this path. Okay, one idea that Ute mentioned at the beginning is actually building on the notion of heuristic, okay, that comes also from behavioral sciences, is this general principle that you can find it in Polya's book on problem solving, in one of the early papers by Marvin Minsky, and also in papers by Julia Pearl, is the idea that if you do not know how to solve a problem P, solve a simple problem P prime and use the solution of the simple problem to guide you in the solution of the original problem P. Actually, this is the main paradigm, I would say, in what is classical planning these days, where basically you solve a problem P prime to get an heuristic to guide the search for a plan in the original problem. The relaxation, this simplification from P to P prime, in the case of planning, is called the delete relaxation. It is actually a monotonic relaxation, where basically every action can change the value of the variables, but actually the variables get new values. They do not lose, okay, the previous variables. So this is what makes these representations monotonic and therefore tractable, okay? So with this monotonic property, okay, the planning problems, okay, become tractable. Then you can solve this relaxed version that is P prime and use the cost function associated with this relaxation as the heuristic function to guide the search in the original problem. So this is a technique that basically makes this search for plans in these huge graphs goal directed. Okay, so now you're searching this graph, and this heuristic function that you derive from the representation of the problem P by relaxing it, okay, provide you this heuristic guidance, okay, to compute plans. In comparison with learners, okay, these solvers, these classical planners, do not need experience on related problems, okay? All they need is a description of the problem to be solved, okay? Like in one of the planning languages. I talked a little bit about this before. Another problem that has been addressed effectively in planning in recent years is the problem of the inverse problem of planning, is plan recognition or goal recognition. Okay, so here in this picture, we have an agent moving away from S. Okay, so there are a couple of arrows that show that the agent is moving, okay, we can see in the direction of B. Okay, from the point of view of plan recognition, so we observe these two moves by the agent, and we want to determine what is the goal of the agent. Is it trying to get to A, to B, to C, or to any of the other letters that we have in this picture? Okay, so, okay, from an intuitive point of view, okay, we can argue maybe going to B, maybe to A and C as well. Okay, it's much less likely that he's trying to get to one of the letters, okay, at the bottom. So the question again is how to do these recognition. So we see the problem, we see the example. So what we need is a mathematical formulation of the problem and algorithms, okay, to solve these mathematics. And it turns out that a big part can be done, okay, by reducing the problem, okay, using Bayes rules or standard rule coming from calculus of probability these days. In Bayes rules, we have that the posterior of the goal, okay, given the observation, is given by this expression that we have with two terms. Okay, the likelihood of the observation. So how well each of the goals G predicts the observation, how likely is each goal a priori, and what is the likelihood of the observations that you got. Now, it turns out that the probability of the observation is a constant, okay, so it's a normalizing constant. You can remove it from the equation, basically. The probability of the goals, you can assume that all the goals are a priori equally likely. So basically, the heart of this expression is telling you so that the posterior will be proportional to how well the different goals predict the observations that we obtain. And it turns out that a goal predicts well the observations according to a pair of cost measures. So you have to compute, so what is the cost of reaching the goal while complying with the observation? What is the cost of reaching the goal G by not complying with the observation? You can complete these two cost measures for every goal, okay, by calling a planner. So at the end, you get that this likelihood and the posterior probability that you want can be computed just using Bayes rule and 2 times the number of possible goals calls to the planner. Once again, okay, this actually is a typical classification problem. So we are trying to classify the behavior that we observe of the observed agent into one of the goals. So we have a finite set of classes, okay, we have some inputs that we are trying to classify. And if you go, okay, through the idea of learning, okay, you will need experience on related problems in order to estimate the probabilities of a new problem. In the case of solvers, okay, all you have to do is to describe what is the pool of possible goals, okay, what are the effect of the actions in the world and so on. And then you can compute these posterior probabilities basically from scratch without any experience on related problem, just in the specification of the model for the particular problem. Just one last example about how to do thinking effectively in the context of planning. Okay, so in the first case, we talk about how to search for paths to the goals, okay, effectively. In the second, how to recognize goal effectively. In this last slide is about how to do exploration effectively. So let's say that you have the graph, but you do not know exactly which nodes are the goal nodes. Or actually, you do not even know, okay, you don't have a representation of the actions. All what you can do is to apply the action in a state and see what the next state is going to be. It turns out that there is a family of algorithms that enumerate the state space in a way that is different from what you have in depth first search or in breadth first search, and that exploit the structure of a state as given by a set of Boolean features. So for this algorithm, okay, all what you need to have, as opposed to breadth first search or depth first search, is a given set of Boolean features that are given truth values by the different states. So in some sense, you have some structure of the states. And the way that IW1, the simplest of these algorithms, use this set of features is that it does a breadth-first search starting from the initial state, and it prunes all the states that do not make a Boolean feature true for the first time in the search. Okay, so it means that this search will expand at most a number of nodes that will be linear in the number of features, while breadth-first search will expand a number of nodes that will be exponential in the number of features. So IW1 is basically runs in linear time, and it's an incomplete algorithm. IWK is a slight variant of IW1, where rather than taking the features as they are, you take conjunctions up to K features and deal with this set of new conjunctive features. It turns out that this very simple algorithm, okay, for instance, an algorithm where you run first IW1, you didn't find a solution, now you run IW2. You didn't find a solution and keep running with increasing values of Ks. So it turns out that there are many, many benchmarks in planning where you can find plans, in particular for atomic goals, and you can prove that this is going to work for values of Ks that are not greater than 2. Actually, okay, this is said that these problems have width 2. So basically, you are finding solutions in exponential spaces, the line exponential spaces, by exploring just a polynomial envelope. Okay, variants of these algorithms have been used with simulators, okay, where there is no action description, but just the game that gives you back, okay, the next state that after you apply the action. One of these versions called Rollout IW1 and was developed as an online planner to play the Atari games directly from the screen pixels as the famous DQN deep learning. Actually, it's interesting to make a contrast between the way that a planner that like Rollout IW1 works and the way that DQN works. Okay, so in terms of performance, okay, they do comparatively well. One of them does better in some games, the other in other games. Okay, but none basically dominates the other. Going back to the idea of learners and solvers, okay, it's illustrated in this case. Okay, DQN takes a lot of training data and a lot of time, and then can play very, very fast, actually much faster than any human can play. On the other hand, the planner, Roll IW1, okay, it plays out of the box, okay? No need any training, but has to think a bit before making each move. So this is illustrating the idea that we were saying before, that learners, okay, we got a lot of experience, okay, slow training, then they work very fast because they have the function f itself. On the other hand, solvers, what they're doing is computing the function point-wise, okay, for the given input, and for this, they need to think a bit. Okay, it doesn't take much, okay, to see some parallels between the ideas of learners and solvers and the ideas of system 1 and system 2. Okay, I talked about this a couple of years ago, but I heard about this, okay, many other people, okay, even people doing deep learning these days. The idea of system 1 and system 2 are normally associated with Daniel Kahneman, that is actually the pioneer of these studies on these dual accounts, okay, of the human mind. The name actually comes from another psychologist, Keith Stanovich, that wrote another book. So Kahneman, it's a Nobel Prize, and now people probably have read this very wonderful book, Thinking Fast and Slow. Okay, Keith Stanovich is the one that actually came up with this name, System 1 and System 2. And he also wrote several books. One is particularly delightful, and I really recommend if you care about not just System 1 and System 2, but about evolution and about the role of System 2 in our lives and in modern societies, okay? It's called The Robot's Rebellion. The robot that rebels in this title actually is not a real robot, but it's us, okay? Basically, his point is saying that it's System 2, the one that allows us to rebel against the program of our genes, okay? So it's fun to read it, and I think it's very informative. Again, so system 1 is the reactive system, okay, normally called the intuitive mind. Is fast, okay, associative and conscious, okay, it doesn't take any effort, it's parallel, and so on, normally associated, okay, with what we the boxes that we associate with learners. System 2 is the analytical mind, okay? It's slow, takes effort, conscious is deliberative, okay? Serial and general and so on. It's a big problem these days that system 2 takes effort, okay? Because of course, many people do not want to make, okay, this effort. And actually one of the points I'll make is not only that we need AI systems, okay, with a system 2, we also need people and societies, okay, that engage our systems too as well. So in terms of challenges, I tend to think that this metaphor of learners and solvers and the relation with system 1 and system 2, it's good for posing some of the key challenges. One of the key differences between system 1 and system 2 in the human mind, learners and solvers in AI, is that systems 1 and system 2 are tightly coupled in the human mind. Okay, in a sense, one is calling the other all the time. Okay, you can read, okay, Daniel Kahneman's book for many, many interesting examples. Okay, on the other hand, most of the research in learners and solvers is going its own way. So in my view, one of the key challenges in AI these days is to achieve this combination of system 1 reactive intelligence along with the ability to think about the specific problems that fall out of the distribution, okay, and one of the key challenges is to be able to learn the models that solvers use from data, okay? So while models normally are built by hand, okay, whether you're working SAT, in planners and so on, so the idea will be, okay, how to learn these models from data alone. For instance, one of these famous deep reinforcement learning programs, DQN, that I mentioned before, okay, learns to play the Atari games directly from the pixels, but it never builds, okay, a high level representation of what's going on. All what you know is what to do, okay, for different states of the screen. So a very interesting challenge there, for instance, would be, okay, how to learn the model of what's going on given the information in the pixels. Of course, you bring a lot of prior knowledge, but maybe you're completely new to the Atari game. So there is a relatively crisp challenge, okay, given by this example about how to do that. Even people doing model-based approaches, okay, using deep learning, normally they are not trying to learn this type of symbolic models that in some sense represent objects and relations as well. Okay, in the rest of the talk, okay, so I think I have 15 minutes, right? Okay, so I try to get a bit more technical and address this particular point. This is about how to learn models from data and how to learn, in some cases, from non-symbolic representations, how to learn symbolic representations, and in another case, okay, how to learn, go from one representation to the other. So there are some distinctions to be made, okay? So it's learning from what and learning for what, okay? In the case of planning, basically you can learn from symbolic information, from non-symbolic information like images, or from black box states, okay? All you know is that one state is different than the other, but you have no access to the content of the states. Okay, that makes a difference about learning for what. You can learn them for model-free control, as in DQN before. You can do it, learn a model for model-based control, or another option that I'll mention as well will be a generalized model for dealing with a whole family of problems. So I'll be talking about a couple of points in this space. In one case, learn a first-order symbolic action model from black box states, okay? First order, what we mean is a representation that involves relations and objects. And in the second is how to learn generalized planning problems from symbolic action models, but that these models will allow you to build not just plan for some instances, but basically general strategies, okay? Something that, again, is something that people normally can do, and planners can do so far, and the learners, okay, don't do it so well either. So let me go to the problem. So before trying to get a formulation, okay, so it's good to illustrate the problem in one particular example. So if you don't follow me with the formulation or with the details, okay, at least, okay, I'll try to convince you that this is an interesting and meaningful problem. Okay, so the question is here. We are given, so we have a graph, okay, a directed graph at the bottom of the slide. This graph actually shows the space structure of a particular problem. This is Tower of Hanoi with 3 disks. Okay, so basically the number of states are the ones that are shown by the nodes here. The transitions that are possible are the ones that are shown by arrows. Okay, so this is the input information that we want. We don't want anything else. Okay, we want this graph. In some cases, okay, we're gonna be happy with some samples of this graph. Let's assume for simplicity that I have this graph. Okay, and what I have on top is a first order description of the actions, okay, in this domain, basically to move a disk from one particular disk to a destination disk, okay? So there are basic number of preconditions, okay, that basically you cannot put a disk on top of a smaller disk and so on. You cannot move disk, okay, on top of itself. Okay, so the target disk has to be clear and so on. Normally, if you want to do planning, you will write this type of action schemas by hand. Then you can apply this schema to any Tower of Hanoi problem, no matter the number of disks, is exactly the same schema, okay? So the question is, can we go from this plain graph showing the state structure of, in this case, of this problem, and derive the generic action schemas, okay, that given instance information, in this case, that you have 3 disks and so on, so extra information that is not shown here, will allow to generate exactly the same graph or not. Okay, so that is the problem. So basically, if we manage to do this, this will be a way to go from non-symbolic information as represented in the graph to symbolic information, not just symbolic, but first order, okay, because it's basically postulating relations and objects, okay, obtained from the non-symbolic information in the input, okay? So this is the intuition for the problem. So let's try to make this problem a bit more precise by defining what is the target language. So the input is clear. So it's a directed graph. In certain cases, we can accept certain labels in the graph. Okay, in the case of Hanoi, we don't need any labels at all. Okay, so we are looking for first order representation, a particular target language. The target language that we use is basically a fragment of what is called PDDL, a standard language in planning, that is first order. Every planning problem in PDDL is given basically by 2 files. Okay, one is the domain file, that is a first order domain, so you have the relations and the action schemas, and there is a separate file that provides the instance information, that is the objects and the relations that they satisfy initially. Once that you give me a problem P, okay, in terms of the domain and the instance information, every P defines a state graph. Okay, so every P defines one particular state graph, okay, where the nodes of the graph are associated with the states of the problem P. The root node is the initial state, and so on. So the question that we want to address is the following. Again, so the technical details do not matter so much. Not all of you are into this type of topics, representation and learning and planning, okay? But at a general level, I think we can all connect to this if we buy the premises, okay? So in a sense, we are looking for a generative model. So we want to be able to generate the graph that we observe using a very compact generative model, okay, that is written in a first order language. So the problem is, so if somebody gives, so a problem P defines a graph, can I recover P, meaning D and I, from the graph? Or if not, so now I give many instances, all sharing the same first order information, D in the domain, and I'm giving you a bunch of different graphs for different instances. Can you now recover this information? Can you go back from GI to the PIs, and in particular recover this first order information in the common domain D? Okay, it's interesting because from this instance, then you can apply this domain as we did in the slide for Tower of Hanoi, for many different instances, an infinite collection of instances, because it works for any number of disks, even though you learn for a few disks as well. So actually, so once that we have the task defined, so basically find the simplest instances PI in terms of domain and in terms of facts, okay, involved in the predicates in this domain and a set of objects. Can we infer these instances from the graph without knowing anything at all about the instance information. It means I do not know the number of objects. I do not know the relations. I do not know the static relations in the domain. Okay, I do not know the action schemas. Can I do that? And it turns out, okay, that the trick is that this is a very good target language, because for most of the domains that we care about, that we normally model, can be characterized in terms of a small number of hyperparameters. So any PDDL or any planning files, okay, for the domain will normally be relatively small, okay? So a given number of action schemas, okay, that is never too large, okay? A given set of predicates that is also it's fixed, each one with its own additive. So the point is that you put bounds on the number of action schemas, you put bounds on the number of predicates and the additives and so on. The problem of learning, going from the graphs to first order representation that accounts for these graphs, turns out to be a combinatorial problem. And if you're looking for the simplest domain descriptions that account for these graphs, okay, so this is an optimization, okay, a combinatorial problem that can be actually solved by weighted max SAT or by running SAT multiple times, okay. Okay, this is what we do in a recent paper with Bly Bonnet. Okay, you can take a look at this paper from this. So eventually I'll give these slides to Ute to be posted, okay, next to the talk. Okay, so things that we can do are like this. So somebody inputs, okay, the graph that you have on top, and in this case, you get a single action schema, okay, with the predicates below. This is not exactly what you have before, okay? Some of the names of the predicates, okay, so are the ones that we are given it by themselves, okay? So this, we are given these names like clear or not, odd, and so on for readability. Of course, okay, these predicates lack any meaning like predicates that are used, okay, in PDDL encodes. They don't come with interpretations, okay? So you can do most interesting things. So here is another benchmark domain in planning where basically packages to be moved between one room and another room. And in this case, so you get sort of a more complex representation. In this case are 3 schemas, but again, so all the input information is in these in these graphs, along with bounds on some hyperparameters. So last example of this, so this is the state space, okay, corresponding to a block instance, I think with 4 blocks, okay, and this is the representation that is obtained with the choice of the names of the predicates that are learned, okay, given by us to make their meaning clear. There is not a perfect match between what we will normally write and what we get here, but the representations are good, meaning if you, for any number of blocks, okay, it is gonna be isomorphic to the graphs that you get with a standard representation. And you can see some of the names are like a block, it's not on the table or it's not equal to another block. So some of the predicates, okay, that are not exactly the one that we normally will write by hand, but can be understood in this way. So as another problem that I wanted to get into, although I do not have much time, so let me just describe what the model is and how it touches the 3 issues that we care about, that is planning, learning, and representation. Though these are problems that basically lie in this intersection, okay, is the problem of computing general strategies for solving problems. Actually, in many cases, when people in learning trying to solve, let's say, planning-like problems, what they're trying to compute is actually a policy that will not only work on the instances used for training, but in an infinite collection of instances that were not seen. So the idea of generalized planning is similar. So we want to be able to compute policies or plans that will not work for some examples, but for a large set of instances, and in many cases, an infinite collection of instances. So think about the blocks world. There is a big difference between solving a particular instance of the blocks world. Okay, the solution is a sequence of actions that go from the initial configuration, takes you to a target state. Is very different, okay, to come up with a general strategy for solving any instance, okay? So the dumbest strategy, okay, but it's simple, is put everything on the table and then build the target towers that we want in order from the bottom up. So this is a general strategy will allow you to solve any problem, not optimally, but not worse than 2 times, okay, the optimal cost. So, and the question is how to get these general strategies as opposed to plans for each specific instance. Okay, in a sense, this form of generalized planning, okay, if we go back to the boxes that I had before, it's like computing the function f itself. Okay, I'm not computing the plan for the given instance, I'm computing the function f itself. Now you give me any instance and I can use this strategy to tell you what to do in this particular instance. So there are many ways in this is connected what normally you want to do in learning from the point of view of planning. So we assume that we have the action representations, let's say the PDDA files, okay? The subtlety is that these strategies should work for any number of objects, any configuration of objects, okay? Different instances have different sets of ground action, different state spaces. So a general question is how to represent these general policies and how to derive or learn them, okay? And these are questions I mentioned not only relevant to planning, relevant to learning as well. Many people in deep learning and deep reinforcement learning are also trying to compute these general plans, but normally they don't work out the theory of what is the meaning of these plans. They base this approach that is essentially empirical. And there is also connection because many of these strategies, okay, have the form of programs, okay? So this is also very related to the idea of program synthesis, and this is addressed, okay, in recent work that has been done in this area called generalized planning. I don't have time, I'm not going to go into much detail, okay, except to illustrate with very simple example. Okay, so this line that we see in the middle, okay, not H and X and so on, these formulas in the line. So basically they are represent a general policy for achieving clear X, okay, where X is any block in any instance of the block's world, no matter the number of blocks that you have, no matter the initial configuration, okay? So basically this is a way, a language for expressing this general policy. The way to read this, okay, to give an intuitive meaning is if, okay, the gripper is not holding any block and the number of blocks above X is 0, then do any action that will make holding true and that will decrease the number of blocks about X, okay? So this is the first policy rule on the left. The second one on the right says, okay, if the arm is holding a block and the number of blocks is about X is still greater than 0, then do any action, okay, in the instance, okay, that will make holding false. So basically holding is what's called a Boolean feature. N of X tracks the number of blocks on top of X. It's what is called a numerical feature. So you can express these general policies in terms of these features. So the question is how to obtain these general features from the action representations, given the goals that you want to achieve, and how to compute these policies. I'm not going to be able to get into this, okay? So there is a formulation, again, by reduction to sum, where you can prove certain properties with a bunch of experimental results. I'll have to skip that, but if interested, okay, take a look at some of these references and ones that are coming now, okay? So here an example, okay, I have to skip, no time, okay? And I think most of you probably are not so interested in the details. So let me start wrapping up, okay? So I'll talk about model-free and model-based AI and about some ideas, again, how to learn models and how to learn, in some case, these symbolic representations directly from non-symbolic inputs, okay? So the message is true breakthroughs in deep learning and deep reinforcement learning, okay? So impossible to take the credit away from that, okay? So, but, okay, the reality is that these methods, for the time being, deliver system one boxes only, okay? And it's very hard to trust system one boxes, okay? They do not understand the world, and we do not understand these black boxes either. So the main challenge, okay, to address these two concerns is to be able to integrate these learning boxes together with more transparent based model solvers, okay? And for that you need tight two-way integration where one is calling the other all the time. Okay, there are many points in the space, in particular if you take the case of planning, so whether you're taking symbolic inputs, non-symbolic inputs, or black box states, what you compute, what the representation that you learn is for, okay, model-free control, model-based control, or generalized plans. And we look at a couple of points in this space, okay, in particular learning, first order planning representation from state graphs, and second, we sketch a little bit the idea about how to learn abstract models that support general planning, okay, from small examples. Okay, so the sort of overall message is there are plenty to do at the intersection of planning, representation, and learning. Okay, so I'll be happy if I manage to motivate some of you to look at this. I'll just finish with last thought, okay? So normally these days, people talk about social impact of AI, so I wanted to take my stand. So may I take a minute, Ute?
Yeah, you can take some minutes, no problem.
Okay, I take a couple of minutes, okay? So these days it's normally, okay, to listen to people addressing ethical and social concern about AI. So let me take a stand on that, okay? Since I talk about system one and system, I've been talking for some time, okay? So I would say, as I mentioned at the beginning, that system two, the deliberative reasoning is not only necessary for systems, AI systems that can be trusted, is essential for people and also for societies, okay? So deliberation, intelligence is social, is not something individual. And even AI, with the AI that we have now, is not at the level of human intelligence. It's true, can be used, okay, for good, okay, or to cause harm. I support personally all the initiatives, okay, about ethical committees and AI principles, but in my view, that's good, but it's not sufficient, okay? This technology is being deployed in a system, okay? And we can see that increasingly markets, politics, they want to sell their stuff and they play with our system one. They're focused on the bottom line, and not too many people is trying to get us thinking and deliberating. And those that do, they lose the elections anyway. Okay, so I'll say a couple of messages, one ironic and one serious. So if we want good AI, I think we need a good and decent society that engages and promote our system too, not just in AI, but our day conversation. And of course, that it cares also about the common good. So being good at reasoning is not good enough. You have to care about the things that deserve care. Okay, and just to finish, normally in many of these discussions, so I add an irony, and I always say, so we need AI for social good because we need artificial intelligence for the social good because natural intelligence is busy in other pursuits. Okay, so that's supposed to be ironic. Okay, but with that, I'll finish. Okay, thank you all for the patience. Mm-hmm.